So in 7.3, we learned about how to write out the equilibrium expression. That's the K equals, and then it's the concentrations of the products multiplied over the concentrations of the reactants, and you raise it to the power of the coefficient. Okay? But when you know concentrations, then we can calculate the constant. So an important thing to know is that you do not have to know what units are for these constants. There are no units. So that's wonderful when calculating and solving for your answers. But so we have example 4, where this is for the synthesis of ammonia, which that is when you have nitrogen gas plus hydrogen gas, and it forms NH3, which is ammonia. Okay, so that's what it's talking about when it says synthesis of the ammonia. And so we're given these concentrations, and they say equilibrium concentrations. In the future, we're going to have to be careful about when it says initial conditions or initial concentrations versus equilibrium concentrations. Okay, so we want to calculate the value of K at 127 degrees for this reaction. Now, temperatures, this unit, are not really that important. It's just important to know that just like rate constants change with temperature, so do equilibrium constants. So when it tells you a temperature, that's just for your information, but you don't actually plug it in necessarily when you're just doing a K expression. So what will be the numerator for this expression? Before we plug in numbers, that'll be the NH3. And then does the NH3 have a coefficient?
2.
As a 2, so it'll be squared. So we'll have NH3 squared on top. And then on the bottom, we'll have N2 to the first power, because there's only a coefficient of 1, times H2 cubed. Okay, so then now we just plug it in and solve. So we'll have, and it is kind of nice the way that they're given to you. You have to be very careful how you plug things in, because you don't want to accidentally cube the wrong thing. So we have 3.1 times 10 to the negative 2 squared over 8.5 times 10 to the negative 1 times 3.1 times 10 to the negative 3 cubed. On my calculators, the exponent button is the y to the x. So just be careful with your order of operations when you're typing in what it is. It should be a pretty big number.
It should be a big.
Yeah, like a big, like thousands.
Mine's
Big.
in the thousands. Well, we get it the same.
Make sure that when if you're putting everything in at once. Okay. Yeah, and then when you do the bottom, be very careful that you have to cube just the H2 and then multiply by the N2 before it all divides. So, like, be very careful with that. Just typing in the calculator is the hardest part. That is correct.
Oh, boom. Hey, I got it.
Good job.
Did I do something wrong?
So that is correct, but not rounded correctly to significant figures. So we wouldn't want to put that in 2 sig figs, so we would say 3.8 times 10 times 10 to the fourth. for correct significant figures.
Could we look at like 38?
You can leave it at 38,000. Yeah, like 38000.
38440. Me too, I got that answer.
Maybe, did you round your numbers?
I wrote the whole thing. I wrote the whole
Oh.
thing down and used those numbers.
Okay. Well, that's still really close, so I don't know. We'll check. We'll look at it. It can still probably.
But even with
3.8,
sig
but-
fix, it would be 38, right?
Yeah. Okay. So that would just be how to do it. I think I might have included an example later. I don't really see. I'm like freaking out. Like there's so much going on with this unit right now in my head. But now this is if you're solving for K. You might have a problem in the book that you have to do where you know K and you know some of the concentrations, but you have to solve for the other concentration. In that instance, just plug in X wherever you don't know and then just solve for X. Okay? So it's just algebra, getting everything by itself, what you need to solve it out. It shouldn't be too hard, just like knowing where to plug everything in is a little bit difficult for people. Okay, so something else to consider. Oh, I left myself lots of room apparently. It applies to most chemical systems. So the law of mass action is just how that products over reactants and raising to the coefficients, how we get that. It applies to most chemical systems in solution and gas phases. Remember, we don't include solids or liquids. We only include things that have changing concentrations. And there are corrections to be made for if you have a very concentrated aqueous solution, so concentrated means a very high molarity, or if you have gases at high pressures. So both of those would be like extra instances that you have to think about. Okay. This table, I included this. I just wanted you guys to see that. Let me go back really fast. So these would be like 3 different trials, all for the reaction we just did. And so the initial concentrations were what were put in initially, and then when it reached equilibrium, this is how they found those values, and then they plugged in and they found the K value. So notice how the K value is the same every time. And the reason why the K value is the same every time in this table is because they're all taken at the same temperature. So that's one of the reasons why it equals each other. If they were at different temperatures, the K values could be different. But this just shows that you could have 3 different experiments that start with 3 different amounts, and still, once you get equilibrium, even though the ratio works out the same, sort of thing. Okay? So that's why I included that. Now this is something, so if you were here yesterday, I said I added something. This is another added, okay? So space that you could write this now, like I would put like a little like star and says like C, the back side of the note packet is currently free. Or if you used up a lot of the back yesterday, I would do it at the bottom of page 9. Either of those places would be good spots. We're going to do an example with after learning this equation. So I don't know how much space you actually have on page 6. Okay. Now I would say you don't have to write everything down, but I just accidentally forgot to include this when I created the notes. So sometimes, remember we said like we have Kc and we have Kp. Kc, or just K, is when you plug in concentrations like molarities. Kp is when you plug in pressure values, usually in ATM. Okay? So we have an equation that relates the two. So I would definitely write down this equation for yourself. Okay? Where the K of the pressure, Kp, is equal to the K of the concentration times RT raised to the change in N. So we have a lot of variables in there that we need to define besides just K and P. And the changes N is the difference in the sum of the coefficients. So it's actually the products minus the reactants to find that. And it's the total coefficients of everything on the product side added together minus everything on the reactant side added together. Okay, then R since we're going to assume that KP, we're going to use ATM most often, the R value that we need to use is 0.08206, because that's liters atmospheres per mole Kelvin. So that's the correct R value. We will use that back in the ideal gas law, back when we talked about gases in unit 3 or 4.
I remember that number.
Oh, we can use it in Chem 1 too. And they're going to learn about it on Monday in Chem 1. And then temperature, we just want to make sure that that is in Kelvin because of the way that the units all work out. Okay, but again, the K and the KP will not have units. Everything should cancel itself out when you plug everything in. So this equation, there's 1 or 2 homework problems that you use this equation for, and so it's just a matter of understanding which K are you solving for. Are you solving for the pressure rate or equilibrium constant, or are you solving for the regular K? And so I have an example where we're gonna see how that works. Okay, are we all good if I move forward?
Yeah.
Okay. So this is just an extra example. We'll have a number after this day. But if the Kp is found to be 1.9 times 10 to the third, we want to calculate the value of K at 25 degrees Celsius for the following reaction. So we're using our Kp equals K times RT raised to the change in N. Okay. We know that the Kp is 1.9 times 10 to the third. We know that temperature is 25 degrees Celsius. So, does anybody know what that is in Kelvin?
Plus 273.
Yeah, plus 273. 298. If you want to be very exact and say 0.15, you can. Okay. And then now, the only other thing, so, and then we know R is the 0.08206, because that's constant. Okay. The only other thing that we need to solve for before we figure out the whole equation is the change in N. So for the change in N, we need to take the total reactants, or total products minus the total reactants coefficients. Okay, so we're looking at the numbers in front. So for products, we only have one product, so that's a 2. Okay, and then for the reactants, we have to take the 2 from the NO plus the 1 from the Cl. So that's really 2 minus 3 equals a -1. Anybody confused about where that came from? Okay, so then now we'll have 1.9 times 10 to the third is equal to 0.08206.
I am confused with that. You can go back to it.
Okay, let me just write this down, and then I'll go back. So this inside the parentheses came from both reactants, because you have to add the entire reactant side together.
Okay.
And the products, there's only one product, so that's why it's just 2.
Then you do product minus. Oh,
Yes.
okay.
Yep. Okay, now if it's a -1 charge, what does that mean mathematically? Like, how can we change this? Yeah, it's going to be the fraction. So I forgot K, sorry. Nobody pointed that out to me. I was like, we're not solving for anything right now. It's times K. So how I made this change so that it works better in my eyes is I put K over the 0.08206 times the 298.15. For me, that helped me mathematically figure it out better. So then now we just need to get K by itself.
Wait, so what happens to the -1?
The -1 means inverse.
Then you do.
So that's why I forgot the K originally. So that's why I just put K on top and then I put that on the bottom.
Sweet.
And this answer is going to be big because if you think about it, 1.9 times 10 to the third is like 1,900. So if it's a big KP, it's also going to be a big K. 4, 6. What'd you say? 6, 2. Okay. Yeah.
So if you, I don't understand why you put it underneath the K. It's like. why
I
would
put it
you-
underneath the K because of this. I was just getting rid of that -1 power. Because that means inverse, right? So I just inversed what was inside the parentheses, the R and the T.
And you multiplied.
Multiply these, and then you multiply that too. And then, okay, so then we'll go back to two significant figures, because that's what we're given in the problem. So 4.6 times 10 to the 4th. Okay. Awesome. So, if it talks about, and I can look up which problem it is that you have to use this equation for from the homework list. But in 7.5, we're going to talk about like when do you get these really big numbers and when do you get really small numbers, because right now it's all just arbitrary. But in 7.5, we'll talk about what does it actually mean when you have a big number, or what does it mean when you have a small number. Okay.